Hello everyone. In this video, let's talk about 2022 AMC8 question 25. A cricket randomly hops between 4 leaves, on each turn hopping to one of the other 3 leaves with equal probability. After 4 hops, what's the probability that the cricket has returned to the leaf where it started? So let's mark these 4 leaves as A, B, C, and D. Now we first recall the definition of probability. The probability is a quotient of 2 numbers. On the numerator, that corresponds to the number of, say, valid passes over the number of or passes. The valid passes sometimes is also called favorable passes. In this problem, the valid passes corresponds to the pass that the cricket starts from A, and after 4 hops, it returns to A. Let's give a name to such pass. So we call it 4-hop returning pass. So in order to find the probability, we need to find these 2 numbers. Let's first calculate the number of all passes. So here, since this hop has the option of 3 choices, for example, if the cricket starts from A, the first hop, the cricket could hop to B, to C, or to D. So the first hop, there are 3 options. If after first hop, the cricket stay at B, now for the second hop, the cricket still has 3 options. It can hop from B to C, to D, or to A. And this is true for later hops. So based on this observation, we can calculate the number of all passes. Three, because the first hop, there are 3 choices, times 3. The second hop still has 3 choices. The third hop, 3. The last hop, we still have 3 choices. Totally, there are 81 different passes. This corresponds to the number of all passes. That is the number in the denominator. Next, we need to find the number in the numerator. That is the number of valid passes. We will use 2 methods to do this computation. To compute the number of valid passes. Method 1 is based on pure multiplication principle. Let's draw these 5 positions. The cricket starts from A and goes to the second leaf after 1 hop, the third leaf after 2 hops, the fourth leaf after 3 hops, and finally, it returned to A. This is a typical 4-hop returning pass. Now let's calculate the total number of 4-hop returning pass. Here, we discussed two cases based on the scenario for the 3 intermediate positions. The case 1, the original position A is not in these 3 intermediate positions. So for these 3 intermediate positions, they are B or C or D, but there's no A. Let's see the number of options for each hop in such case. Notice that for the first hop, there is no constraint. The cricket can hop from A to B to C to D. There are totally 3 options. That's the first hop, 3 options. Now we'll consider the second hop, because now the cricket is at B, C, or D. Let's see, it's at B. The next hop, the cricket cannot return to A. So the cricket can only hop to C or D. There are only 2 options. This is the second hop, 2 options. For example, for the second hop, cricket hops from B to D. Now we consider the third hop. The third hop still, the cricket cannot return to A. There are only 2 options, from D to C or from D to B. So there are 2 options for the third hop. Finally, for the last hop, it returned to A. There's just 1 option. So this case corresponds to the following number. 3 times 2 times 2 equals 12. There are 12 such 4 hop returning paths. Let's just one example here. One example such 4 hop returning paths. For example, from A hops to B, and from B hops to D, and from D hops to C, and from C finally hops back to A. So this is one example. There are totally 12 such passes. Next, we consider the case 2. For case 2, the original position A is in these 3 intermediate positions. And if that's the case, this A must be in the middle. So A must be in the middle. Now let's consider how many such passes there. A, B, C, and D. For the first hop, it's totally free. The cricket can hop from A to B, from A to C, or from A to D. That means there are 3 options. As claimed, the next hop, the cricket is returned to A. That's the middle position A. For example, it hops from B back to A. Now we consider the third hop. It starts from A again, so there will still be 3 options. So A can hop B to C or to D. So there are 3 options for the third hop. So finally, it hops back to A. In this case, we have the total number to be 3 times 3 equals 9. One example is as follows. It hops from A to B, and from B back to A, and next from A, say to D, and finally from D back to A. So this is the example. Now we combine case 1 and the case 2. In case 1, there are 12 passes. In case 2, there are 9 passes. The total number of valid paths is equal to their sum, which is 12 plus 9, 21. Accordingly, the probability equals 21 over 81, which is equal to 7 over 27. Next, let's consider method 2 to calculate the number of valid passes. This method is based on recurrence relation. We define number, let x4 to be the number of 4 hop returning passes. Actually, this is what we are looking for. And similarly, we can define x3, that is the number of 3 hop returning passes. Let's consider their relations. For valid 4 hop passes or 4 hop returning pass, like this picture, we have the following claim. The middle 3 are 3 intermediate position. The claim is that the first 3 hops of a 4 hop returning pass must not be a 3 hop returning pass. And vice versa. So this is an equivalent description of 4 hop returning pass. That is, the first 3 hops, it must be not a returning pass. In other words, the 4th position here is not A. The cricket can only hop from a not A leaf to A. For example, the cricket hops from A to B, and hops from B to C, from C to D, and back to A. So here, the last hop is from D to A. So that is not A. D is not A. Or It hops from A to B, from B to A, and from A to C, and from C to A. Still, the fourth position is not A. In this returning 4-hop returning path, if we consider the first 3 hops, it's not a returning 3 hops. That's the equivalent description of 4-hop returning path. So we can find an equation connecting x3 and x4. Accordingly, the number of 4-hop returning paths this is x4 equals the number of 3-hop not returning paths. So this part is the total number of 3-hop passes, which is 3 cubed, minus 3-hop returning passes, which is x3. This leads to equation, which is called recurrence relation. X4 equals 3 cubed minus x3. Similarly, if we denote xn to be the number of n-hop returning paths, we still have similar recurrence relation. That is, xn plus 1 equals 3 to n's power minus xn. We can use this recurrence relation to calculate x4 from x1. Clearly, we have x1 equals 0 because the cricket starts from A and it arrived at somewhere not A. By the recurrence relation, we solve x2 equals 3, the first power minus x1, which is 3. And then we got x3 equals 3 squared minus x2. That is 6. Finally, we have x4 equals 3 cubed minus x3. That is 21. Accordingly, we can get the probability to be x4 over the total number of passes, that is 81, which is 21 over 81. It can be simplified into 7 over 27, which is the answer here.